Welcome back. In the last video, we described how to multiply matrices just using an example. We had a 2 by 2 times a 2 by 2, and we learned that that matrix multiplication involves doing a bunch of dot products, taking a row of the first matrix in the product and dotting it with a column rather of a matrix of the second matrix in that product. Some notation. Notice that when we had A multiplied by B, there was no dot between them or no X between them. There was no symbol at all. And that's typical. That's how we describe matrix multiplication. There's no symbol between the matrices when we multiply. The other piece about notation is something that we borrow from exponent notation. If you put a transpose or power, we'll talk about powers very soon. If you put a transpose or a power on a matrix, that transpose or that power only applies to that one matrix. If you have a product, A times B, and there's a T, a transpose on the B, that transpose only applies to the B. It does not also apply to the A. If you want it to apply on both things, you need to put brackets around it. So A times B all transposed, if you want that instead of A multiplied by just B being transposed, you need brackets to indicate that. It's actually better to circle those two because that's how we would typically write A multiplied by only B being transposed compared to A multiplied by B and then that being transposed. Oh, I don't even have something really important here. This is not really a secret note. This is in the textbook, and it's absolutely necessary to solve some problems. But very important property is that AB transposed is not equal to A transpose B transposed. Instead, what happens is A times B all transposed is equal to B transposed times A transposed. Think about why. Why is it that if I take two matrices and multiply them together and then transpose that, it's not equal to the first matrix transposed times the second matrix transposed? So I'm not going to prove that in terms of the I and J notation. I'm just going to motivate it with an example. Suppose A is 3 by 5. B is 5 by 7. Then A times B is 3, 5, 5, 7. The 5's cancel. We get 3 by 7. So A is 3 by 7. AB is 3 by 7. And AB transposed is 7 by 3. But A transposed B transposed is 5 by 3 and then 7 by 5. It's undefined. And B transpose A transposed is, well, B transpose is 7 by 5. A transpose is 5 by 3. It's 7 by 3. The size, at least the size matches what would happen if we multiply the matrices first and then transpose them. So this is not a proof. It's not a proof that the elements are the same, but it is a proof that at least the sizes are the same. To prove the elements are the same, you have to use the IJ notation. And if you're taking a math course after this, Math 1600, you have to be able to think about the proof in terms of I and J for that course. But we'll skip over that. Okay, so we know that matrix multiplication, if it's permitted, will create a new matrix. And we know what the size of that new matrix is going to be based on the input sizes of the matrices that we're multiplying. And we also know from just thinking about that size condition that matrix multiplication cares about order, unlike number multiplication. So A times B is not necessarily going to be the same thing as B times A. Let's next look at a type of matrix multiplication between row vectors and column vectors, which is a multiplication form that we've already done in our preview of matrix multiplication when we're taking a row multiplied by a column. So I put little squares here, just indicate it doesn't matter what the numbers are, independent of the values there. If the shape is one row, we call it a row vector. If the shape is one column, we call it a column vector. If we're asked to do a matrix multiplication between a row and a column, then we can treat it like a dot product. We can say that the result will be a number, and well, it'll be a single element of a matrix if we do matrix multiplication. But if we treat it like vector multiplication, like a dot product, we'll get a number out, and the value of that number will be what any value of a dot product would be. It would be the first times the first, plus second times second, plus third times third. So in this example, that's what we're going to do. We're going to treat this as the dot product between 5, 2, 3 and 0, 1, 5, which is 5 plus 2 plus 15, which is 22. And I'll put square brackets around this because this is actually a matrix. It's a 1 by 1 matrix. When we do multiplication of a row and a column for matrix multiplication, that's a legitimate dot product. We actually convert them into vectors and do a dot product and get a number out, and that number gets input into the matrix. This is just being pedantic to put that bracket there. I don't want to put it in the same color. It's very, very picky to say a single element, a 1 by 1 matrix 22. But it is, because a matrix times a matrix always gives you a matrix. All right, next we'll look at some operations. We're asked to multiply A times B, B times A transpose, and C transpose C, where all these quantities are defined. So I'll make 3 columns here. First one, A times B. Well, we're not told what B is equal to. We're told that what B transpose is equal to. So we can get B by transposing B transpose. B is equal to, I didn't write this down before, B transposed, transposed. If you transpose a transposed matrix, you get the original matrix back. Because you're flipping rows and columns, and then you're flipping them again. So I'm just going to flip the rows and columns, 3, 4, and now it's back to the original. Because the 3, 4 row is the transpose of the original. So we just transpose it to get the original back. So now I'm going to do the matrix multiplication between those two objects. 1, 2 multiplied by 3, 4. And it's a row times a column dot product. We'll put the number inside a matrix. We get 1 times 3 plus 2 times 4. We get 11. Okay, next, B times A transpose. And we don't have A transpose, so we'll get that. We have B 0, -5, 2, 5. And then A transposed. One, 0, -3, 2, turning that row into a column. So I'll put that here. 1, 0, -3, 2. And we're doing a row times a column. So we're going to get a single entry. We have 0 times 1 plus -5 times 0 plus 2 times -3, so -6, plus 5 times 2, 10. So we get the single entry matrix, 1 by 1 matrix, whose entry is 4. And the last one, C transpose times C. C transpose times C. So that's going to be C transposed is what's already given, 5, 0, -3. And then C is what we get if we flip it. Turn the row into a column, 5, 0, -3. So now we do number times number, 5 times 5, 25, plus 0 times 0, plus -3 times -3, so positive 9. And we have an entry, single element matrix, 1 by 1 matrix, whose entry is 34. Again, every time we do a row times a column operation, what comes out is a single entry matrix, 1 by 1 matrix. All right, now we did that preview of matrix multiplication, and the reason I did the preview before actually defining the operation properly is because the definition is given on the slide and it looks scary. That Cij, the ij entry of the new matrix C, capital C, is equal to AI1 times B1j plus, and then it just goes on. I'm not going to read it. What's going on here? Like, what is all this? This is the long way of writing a dot product between one of the rows of the first matrix and one of the columns in the second matrix. It's just a dot product. If you truly want to understand matrix algebra, you're going to have to take another course, Math 1600, where you dig into that ij notation much more closely. I am not going to torture you with the ij notation inside this course. This is meant as a first course in matrix algebra. You've never seen matrices before, you've never seen vectors before. So for us, for this course, we're going to treat it like a dot product, that the Cij entry is equal to AI, so row number I of the first matrix, times column number j of the second matrix, which is perfectly equivalent to the big mess that's above, but it's so much cleaner and neater and easier to think about. So to give you another picture, another visual representation of matrix multiplication, if I take the first row and multiply it by the first column, I get C11, the 1, 1 entry of the new matrix. If I take the second row and dot it with the first column, I get the 2, 1 entry. So row 2 times column 1 gives me the row 2, column 1 entry of the new matrix. It has that nice property. Then I go with the third row times the first column, then I get third row, first column entry. Fourth row times the first column, the fourth row, first column entry of the new matrix. And then the last, row 5 times column 1 gives me the 5, 1 entry of the new matrix. Now if I go back up to the top, row 1, and then move 1 to the right on the second matrix and take the dot product of the second column, then I get row 1, column 2 of the new matrix. And then march along. I'm not going to bore you with every single one. If I want the 3, 3, then I do row 3, column 3. If I want the 5, 4, then I do row 5, column 4, and so on, until I do all the dot products that are necessary. And that is matrix multiplication. Okay, so the first example that we're supposed, like that's kind of in order. The first example that's in sequence is we want A times B. And I like making a copy of the question so I can highlight it easier and color it. 1, 2, 1, 1, 3, 2, multiplied by 1, 2, negative 3, negative 1, 2, 4. And let's find out what the size is going to be. So we know ahead of time what's going to happen. We have a 2 by 3 times a 3 by 2, 2 by 3, 3 by 2, we're going to get a 2 by 2. That means, because there's going to be 4 entries, we will have 4 dot products. If the new matrix was 5 by 2, that would mean we would have 10 dot products. We'd have 10 entries, each entry defined by one of the dot products. So I'm going to put this down below, put a space for a 2 by 2 matrix, and then get out your colors. Just do it one more time, and then after that you can abandon using colors. I'm serious. I'm serious. Like, do this with colors. First row, first column. C11 is equal to 1, 2, 1 dot 1, negative 3, 2. So that's going to be 1 minus 6 plus 2, which is negative 3. So negative 3 is going to go here. Now I'm going to do the next one. First row, second column, the different color. C12 is equal to 1, 2, 1 dot 2, negative 1, 4. So 2 minus 2 plus 4, we get 4. Okay, now I'm going to do second row, first column. That's going to be the C21 entry. 1, 3, 2 dot 1, negative 3, 2. So we get 1 minus 9 plus 4, which is negative 4. So that goes here. And then we have one more entry. Row 2 dot column 2. That's the C22 entry. 1, 3, 2 dot 2, 1, negative 1, almost made a mistake. And there's probably mistakes in this video because I miscopied stuff. Just email me. 2 minus 3 plus 8 is 7. And that's our answer. So we created a new matrix. It's 2 by 2, so 4 entries. Each entry came from a dot product, and they're all color coded as indicated here. And let's see, what do we do? Oh, we can't do this one in 1 minute, so we'll stop and go to the next video.